In my previous video, I described what is meant by a water flux. First of all, we started with a water flux through an open area, and then secondly, through a closed area. If there are no sources of water or sinks of water within a closed area, then the total amount of water flux is equal to zero. In other words, the amount of water going into that area is the same as the amount of water coming out. In order for the total flux to not be equal to zero, however, you have to have either a source of water within that closed area, such as, for example, a faucet, or a sink of water within that closed area, such as a drain. Okay, we now extend these ideas to describe an electric flux. Okay, so now let me go ahead and immediately draw some electric field lines, like so. These electric field lines we'll just write as E, and then let me describe, first of all, the electric flux in terms of an open area. So let's say, for example, like so, we've got some type of open area A. So then therefore, the electric flux through that open area is described by the following expression. First of all, electric flux is labeled as phi sub E, and then as an open integral is the integral of E dot dA. So it's essentially the electric field multiplied by the area. Okay, now let me redraw the diagram, but in this case, specifically in terms of a closed area. Okay, so once again, we've got some field lines like so. Okay, and then let's say that right here is a closed area, like this. Let me specifically label it as such. And then therefore a flux integral would have the following symbol like so to indicate that we're talking about the electric flux through a closed area. Or the diagram that I have drawn, the electric flux through this closed area is equal to zero. Think of it merely in the following way. We've got the same number of field lines going into the area as we do coming out. Therefore, the flux integral itself is equal to zero. In order for the flux integral to not be equal to zero, we would either have to have a source of field lines within the closed area or a sink of field lines within the closed area. What could act as a source of field lines, analogous, for example, to a faucet when talking about a source of water? A positive charge. And the reason for that is because recall that by definition, the electric field lines radiate outwards from a positive charge. So then therefore we could think of a positive charge as a source of field lines. What would then be a sink of field lines? That would be a negative charge. This would be analogous to a drain of water, for example, because recall that field lines radiate towards a negative charge. So then therefore, if you have a charge itself within this closed area, then this flux integral is not equal to zero. The amount of electric flux directly depends upon how much charge is enclosed within the closed area. This then leads us to a fundamental relationship. The first of four equations, were collectively referred to as Maxwell's equations, that describe all electromagnetic phenomena and their application in the entire universe. The first of these four fundamental relationships is referred to as Gauss's law. So now let me take you through a description of Gauss's law. Gauss's law is considered to be fundamental to nature. It's more fundamental to nature than Coulomb's law is. As you'll see a little bit later on, Coulomb's law is actually a specific application of this more fundamental relationship referred to as Gauss's law. Let me describe it to you in terms of, for example, say a positive charge. Okay, so right here is a positive charge, Q, and then recall, of course, that the field lines radiate outwards from that positive charge. That is like so. Let me draw some field lines. This. And now let me go ahead and enclose this charge from within a closed area, like so. So here's a closed area surrounding that charge, and we now refer to the charge itself, by the way, as Q enclosed. The amount of electric flux that is passing through this area directly depends upon the Q enclosed. In other words, the greater the amount of charge, the greater the field lines, therefore the greater the electric flux. Just think of it that way. So then therefore the electric flux itself, the closed integral like so, is directly proportional to the charge that is enclosed within the closed area. The closed area itself, by the way, is given a name. It's referred to as a Gaussian surface. So then therefore the amount of electric flux directly depends upon the Q enclosed within the Gaussian surface. Now this is a proportionality. Let's go ahead and write it as an equals sign. When we do, we obtain another fundamental constant, one of nature's fundamental numbers. This fundamental constant literally describes the magnitude of an electric field in a vacuum in a fundamental way. Much like, for example, capital G, the universal gravitational constant describes the force of gravity throughout the entire universe. This is a constant that is similar to that in nature. The constant itself is written in the following way. It's written as the Greek letter epsilon, and then there's a little naught symbol associated with it. This fundamental constant is given a name. It's called the permittivity of free space. So epsilon naught is called the permittivity of free space. It's a fundamental constant that describes the magnitude of an electric field in a vacuum throughout the entire universe. The value of that fundamental constant is as follows. It's rather small. This number here, and in metric SI units, the units are as follows. Coulomb squared per Newton meter squared. A little bit later on, we'll see exactly where these units come from in a specific calculation. Once again, this expression right here is fundamental to nature. This expression here is known as Gauss's law. Okay, what we do throughout the remainder of this chapter, that is chapter 22, is we use Gauss's law to evaluate situations involving symmetry to calculate, for example, the magnitude of electric fields. We'll apply Gauss's law to some of the problems that we saw earlier back in chapter 21 when talking about Coulomb's law. But before we get to those calculations, let's just take a look at this portion of the expression. That is, the electric flux through the Gaussian surface directly depends upon the Q enclosed. We'll do so in the context of an example. Go ahead and copy this example down into your notes. It involves a rather complicated diagram. Let me go ahead and draw that diagram here on the board. Do the same in your notes. Okay, now I'm going to do some erasing here. Okay, for the diagram that is given, we are to calculate the electric flux through the following surfaces. Okay, so first of all, right here is a point charge, Q1, and then we surround it with a Gaussian surface like so that's referred to as surface number 1. Okay, then here's a second charge, Q2, and we surround Q1 and Q2 by another surface like so. This Gaussian surface here is referred to as S2. And then lastly, we have a third charge over here. This is Q3, and then we've got a third Gaussian surface like so that surrounds all three of the charges. We'll refer to this as S3. Very simply, all that the problem is asking us to do is calculate the electric flux itself through the three surfaces. Now, we don't have to do a complicated integral in order to make this calculation. The reason why is because the electric flux itself through a closed surface, well, it depends directly upon the Q enclosed within that closed surface. So then therefore, we're only worried about this portion of the expression that describes Gauss's law. So now let's take a look at surface number 1. For surface number 1, the electric flux through that surface only depends upon Q1 because Q1 is the only charge that is enclosed within this surface. Well, what about Q2, you may be saying to yourself? Well, for Q2, its electric field lines, well, those electric field lines pass through completely surface number 1. That is, for Q2, its electric field lines going into surface number 1 is exactly the same as the number of field lines coming out of surface number 1. So then therefore there is no total electric flux due to Q2. It only depends upon the source of the field lines, in this case, due to Q1 when calculating the electric flux through surface number 1. So then therefore the answer very simply is this. The electric flux is equal to Q1 over epsilon naught. Simple as that. Watch me repeat this procedure now for surface 2 and then surface 3. Okay, well, for surface 2, which is right here, the total amount of charge that's enclosed within this surface is Q1 and Q2. So then therefore add them together. The electric flux through surface number 2 is equal to Q1 plus Q2 divided by epsilon naught. So the electric flux itself, never mind the integral itself is actually used to calculate the electric field magnitude. We'll get to that later. Never mind the integral, the electric flux itself just directly depends upon the Q enclosed, nothing more than that. And then lastly, surface number 3, you get the idea here. Surface number 3 is enclosing Q1, Q2, and Q3. So then therefore the electric flux through surface number 3 is Q1 plus Q2 plus Q3 over epsilon naught, like so. Okay, in the next video, this is then where we start to lead you through the process of calculating the electric field magnitude by directly applying Gauss's law and taking a look at the integral itself.